All right, hello everyone. Welcome to Kareem's Chemistry Corner. Oh yeah. We're going to do some light calculations today, figuring out the energy that's associated with particular wavelengths of light, and then we're going to do some unit conversions that might be helpful for those kinds of problems. So let's get started with what is the energy associated with a microwave that has a wavelength, or rather, sorry, a frequency of 7.91 times 10 to the 10 per second. You'll usually see frequency as either an F or a nu. I can't draw a nu, so that's why I've drawn an F there. So how do we actually do this calculation? Well, pull out our handy dandy formulas, which are basically all we need for this problem. This formula in particular is going to be useful for this problem, so we'll use that. We'll use E equals HF. We have F, that's this, that's going to go into right there, and H is actually a constant. This is called Planck's constant, or Planck's constant, and that is equal to 6.636 times 10 to the negative 34. Okay, and this is in units of joules seconds. And the reason for that is because once we multiply joules seconds by seconds, or per seconds, we end up with just joules, and that's what we need for energy. So we have E equals 6.636 times 10 to the negative 34 joules seconds times that frequency, which is 7.91 times 10 to the 10 per second. Okay, and when we plug that into our calculator, we get 6.636 times 10 to the negative 34, and we multiply that by 7.91. We'll use some parentheses actually. If your numbers are off, then make sure you're sticking your parentheses in there, because that's how the calculator actually knows what you want to calculate. So then we have 7.91 times 10 to the 10, and then we get 5.24 times 10 to the negative 23 joules, because we have this seconds cancel and this seconds cancel. And so that's the energy that's associated with this microwave. Very small amount of energy. That's because microwaves are not ionizing. You should make sure that you remember the trend of the fact that if we have a large wavelength, that's going to be low energy. And if we have a really short wavelength, we're going to have high energy. This is a very long wavelength. Just take my word for it, I guess, for now. But if you wanted to do that calculation, you could use this formula, C equals lambda times F, to figure out what the wavelength is. Okay? Let's move on to a slightly more complicated problem. So this one is with light. Actual light this time. So with actual light, you're normally given a wavelength that's in units of nanometers. And this is a problem because the formula that we have, which is E equals HF, and I'll just do a very quick rearrangement of this. I'll use the fact that C equals lambda F to rearrange C over lambda equals F. And so then if we follow this rearrangement, we plug F back into here, then we get E equals HC over lambda. And we no longer have F in there anymore. Okay, so this is how we would calculate the energy using a wavelength rather than a frequency, which is what we have in this case. Okay, so what we actually need to do first is convert our 400 nanometers, because here our lambda is actually in units of meters and not in units of nanometers. So we have to convert our 400 nanometers into meters first. We do that by using the conversion factor of 1 meter is equal to 10 to the 9th nanometers, remember what you want is on top and what you have is on the bottom. We have nanometers, so we end up canceling nanometers. And so if we do this calculation, 400 divided by 10 to the 9, we end up with 4 to the negative 7, kind of unsurprisingly, meters. And that's our wavelength. And so all you have to do is take this wavelength and plug it into this equation up here as that lambda. So then we end up with E equals hc over 4 times 10 to the negative 7 meters. Okay, and so we have our hc. hc is equal to 6.636 times 10 to the negative 34 joules, oops, it's just joules seconds. And then we have c, and c is equal to 300 million meters per second. Okay, and if that's something that's easy to remember, that's great. But something that's a little bit more useful is it's actually equal to 3 times 10 to the 8 meters per second. Okay, so we plug those in, 6.636 times 10 to the negative 34. Multiply that by 3 times 10, 3 times 10 to the 8th. And divide that by 4 times 10 to the minus 7. We end up with 4.977 times 10 to the negative 19 joules, right? Because we have joule seconds up here. So this is the energy associated with this wavelength. So if we compare that to the original calculation that we did, which was right here, I'll just box that for you. If we compare these two to each other, they're off by about 4 orders of magnitude. Okay, so that's why the energy compared to a short wavelength is much, much greater than it is for a long wavelength. So 4 orders of magnitude for a way, way shorter wavelength. Okay, and light is definitely much shorter than a microwave. I believe a microwave wavelength is about 6 centimeters or so. And so 470 nanometers is way, way, way shorter than that. And we can see that based on the energy. Okay, so light has more energy than microwaves. The greater the wavelength is, the lower the energy is. The lower the wavelength is, the higher the energy is. Okay, make sure that you remember this trend very well, because that's super important. Okay, so if we're ranking, for an example, let's say that we had blue light, we have red light, we have IR, infrared, we have UV, and then we have, let's say, X-rays. You could memorize the wavelengths of these, or I'll just tell you what they are, just so that way we can have a proof of concept here. So blue is about 450-ish nanometers. Red is about 600-ish nanometers. These are just ballpark numbers. IR is about, let's say 750 nanometers. UV is less than 380 or 400 nanometers. And X-rays are way, way less. I think these X-rays are about 3 nanometers or so in wavelength. So if we were to rank these based on their wavelength, we would say which color, right, color in quotes, because some of these we can't see, but which wavelength has the highest energy, it would be X-rays. So that would be, X-rays would be the first one. The second one would be UV. That would be 2. Then we have IR, red, and blue. So IR is longer than red, and red is longer than blue, and blue is longer than UV. So that's why blue is going to be 3. And then if we have our red, that's going to be 4, and then IR is going to be 5. And so this indirect, or rather inverse relationship that you have is important, and it can be seen in the actual equation itself of E equals hc over lambda. So energy and wavelength are inversely proportional to each other because the lambda is down here and the energy is up there. Okay.